Good morning, committee, colleagues, and fellow researcher. My name is Nuttakorn, a PhD student from Department of Mechanical Engineering at Kasetsart University. Today, I'm honored to present our research on heat transfer enhancement of the heating plate using air ultrasound. Let's start with the introduction. This RRI shows the forecasting effect of the ultrasound. In our study of the aeroacoustic wave, the dominant effects are the heating and acoustic steaming. Next figure demonstrates the acoustic radiation, showing the pressure node and the antinode of the standing acoustic wave generated by the ultrasonic transducer. The third figure summarizes the propagation of the ultrasonic heat transfer. The enhanced highlight the low frequency and high frequency zones. The last figure illustrates the acoustic wave effect in the closed-loop water system, including acoustic convection, the bubble generated here, and the acoustic steaming, the induced flow by the transducer. Our research addressed three critical questions. The first one, can aeroacoustic wave enhance heat transfer on the heating surface? The second one, how is the heat transfer intensity distributed across the heating surface? And the last one, can we develop a prototype of the ultrasonic transducer integrated with the air condensing unit? The experimental setup includes a closed acrylic chamber with a 20 kHz and 40 kHz air ultrasonic transducer positioned above the heating plate. The temperature measure were conducted using the T-type thermocouple on the surface and the infrared camera. The next slide shows the coordinate system arrived with the elliptic 64. The X is a parallel and the C is a perpendicular to the current direction. Y is the distance from the transducer to the heating surface. Key equation for correct Nusselt number here and the heat transfer enhancement coefficient are shown here. Those four videos capture the temperature distribution after activating the ultrasonic transducer at the heating surface center. The purple and black region indicate the lower temperature reflection heat, high heat transfer enhancement. The uncertainty analysis using the second power method. The maximum uncertainty in the heat transfer enhancement coefficient were less than 6%. For the validation, deviation between the experimental and the theoretical Nusselt number was less than 5%. Those show the confirming setup reliability. The dashed line marks the ultrasonic transducer activation and deactivation. Results show the transient dimensionless temperature reduced of the 15.4% and 40% for 20 and 40 kHz. Demonstrate the rapid heat transfer enhancement of the aeroacoustic steaming. Here, the 20 kHz transducer achieved 38% enhancement at C star of 0.4. The 40 kHz air ultrasonic transducer peaked at 29% enhancement at the center of the sheet heating. This confirms that aeroacoustic steaming disrupts the thermal barrier, bruising the natural convection. The next is a conclusion. The ultrasound enhancement heat transfer for the 20 kHz and 40 kHz could improve the performance to 28% and 29%. The effective enhancement zone in both frequencies were within the half wave range from the center of the heating surface. This technology could reduce energy consumption and enable the compact thermal system aligned with the SDG 7 and SDG 9. The prototype developed integrate ultrasonic transducer in air condensing unit as shown in those figures. Thank you for your attention to our research.